So good afternoon everyone, this is Arun Sharma from Midas here to present the webinar on precess concrete girder design in Midas Civil as per AASHTO LRFD. So this is a quick overview about how we'll be proceeding today. We'll be starting with the model file which is already created, and we have the geometry generated there with construction stages, tendon profiling, and all the loadings have been applied, including the time dependent material properties. So we will quickly review how is the geometry, what are the construction stages, how are the tendon profiles laid down, and what is the different ways of running different type of loadings, and then the material properties. After this, we'll apply the reinforcement to the sections and consider it during the design. We'll modify the construction stage analysis control data as well as main analysis control data will be modified to consider the effect of reinforcement. After this, we'll perform the analysis, which will be primarily live load and construction stage analysis. After this, we'll move on to precess concrete design, how the program checks the sections against failure as per clauses given in the code, and then show the results for the same. So this is how our bridge will look like. It's a 3-span box girder bridge. We have supports right underneath it. It's a single cell box girder, as you can see here. We'll apply, we have the temperature loading applied onto this box girder, and we have applied a temperature gradient, and it's basically a non-linear temperature gradient. It is varying with different depth, and the values are shown right here for negative and positive loading. And we'll also apply wind loads, or we have already applied wind loads onto the structure. We'll quickly review them. So there will be this wind load acting onto the structure. So what we'll do is apply the load onto the girder offset, and consider its bending moment also on that point. So I'll show you where are these options available and how to use them, and the calculations of the value are given right here. And all these things are given in detail in the tutorial that are given on our website under PSC girder design as per AASHTO LRFD. You can download these from our website and try it at your own time. Then we'll add reinforcement data to these sections, which will have longitudinal reinforcement, shear reinforcement, as well as one-legged stirrups in the webs, as you can see here. So this is how we'll be proceeding in the today's session. So let me start by opening the model file, which is already prepared. Let me turn on the solid view so that you can see the geometry right here. Alright, so let me quickly first review how the construction stage is laid down. So if I go to construction stage 1, you can see just one span erected, and along with this, let me display the boundary conditions and also display the tendon profile points. So this is the first construction stage. Then second construction stage, we have the another set of tendons in the second span, then the third span, and then finally the fourth span. The fourth construction stage. So this is how the construction staging has been done, laid down, and the tendon profiles are uh, applied. And this type of model can be easily generated in no time using um, uh, the structure wizards that we have. Something similar to this can be generated using just MMS bridge wizard or FSM bridge wizard. We also have a pre-stressed concrete bridge wizard where you can give so many variations for the spans and the cross section. So you can go and enter the section in the reinforcement data right here. This is a section, this is the reinforcement data. So using these different type of wizards options that we have, you can easily generate this kind of bridge in no time. So today I'll not go into details of how this model was created, but focus more towards the design portion of this bridge. And let me show you the wind loads that are applied onto the structure. So you can just right click, go to display. If I go to the side view, you can see that there is, let me rotate it dynamically. So you can see that there are two loadings. One is the axial, the transverse loading, and one is the moment, which is coming due to the lever arm of the wind load. So you can, and how we achieve this kind of loading is you right click, go into loads, and the loads you go to nodal loads, where you can select the load case and load group name, and then you can apply directly what loading you want to have in what direction and what moment you want to have. This is a nodal load. Similarly, you can apply it as a continuous load onto the entire length of the bridge using element beam load, where you can specify what is the you can apply in two folds. One is the UDL, and then you can select uniform moment and torsion. So you can then in the same manner select the entire girder and apply the moment at all the locations. Other than this, there is one more thing you can do to automatically consider the moment and the wind loading onto the structure, and that is that comes through under uniform load if we consider some eccentricity. So if we calculate the eccentricity of the wind loading onto the structure, then the program will automatically apply the wind load at that height and convert it into and calculate its lever arm and apply that moment onto the main girder. So that is automatically taken care of using this eccentricity feature. And same way we can apply temperature gradient to the structure. So right click, go into loads, and there you can find temperature loads, and then you can see temperature gradient. You can see beam section temperature. So let me show you what is temperature gradient. In temperature gradient, you can specify the variation about the local y-axis of the section and the local z-axis of the section, and you can set the temperature range for different heights. So you just need to give the difference here, and the program will apply that much variation from the top to the bottom of the cross section. So this is a uniform temperature gradient, but if you want to have different temperature gradients at different intervals of height, you can choose beam section temperature, where you can specify whether you are working in the whether it's a pre-stressed concrete section, and for top layer you can specify at different heights what temperature gradient should be, so you can apply that kind of variation directly onto the sections. And this type of variation can be taken care in two axes. And with respect to bottom and top, you can apply onto the structure. Let's say for the top you are taking the reference point at the top fiber, you can start by applying it from the top fiber. and if you want to apply from the bottom fiber, you can just change this reference point to bottom and apply it, and you can specify the temperature differences. So in this manner you can apply different heights, what should be T1 and T2, and then click add, then change the heights T1 T2, and thereon you can apply different layers to the same sections. So this is how the loading was applied to this bridge. And let me switch to the initial view here, and then the live load. So I can just right click and display all the lanes on the structure. Let me go to the top view and zoom in here. So you can see there are lane 1, C1, C2 and lane 2. So basically we have defined 4 lanes. Out of these 2 lanes are overlapping to a certain extent, and these 2 lanes are overlapping to a certain extent. The reason we have done it in this manner is when we define the moving load cases, we have made 2 separate load cases, I mean 2 sub-load cases within the one load case. Is a certain set of vehicle will run on C1 and C2. The program will run it on C1 only, then C2 only, and then C1 and C2 together, and get the worst case scenario. After this, the program will run the that given set of vehicle on lane 1, then lane 2, and then lane 1 and lane 2 together, and then get the worst case scenario. Now since we are treating these 2 subload cases as independent, the program will compare which one gives the worst case scenario of the 2 at different sections, and then the program will create the envelope result based on these 2 subload cases, treating them as independent. So the vehicles are not simultaneously applied to lane 1, C1, lane 2 and C2, but they are applied in lane 1 and lane 2 and C1 and C2. So you can have these kinds of variations, or you can create these kinds of lanes anywhere and choose in any permutation combination how you want to the program to apply the vehicles. Alright, so this was just reviewing what we already have in here. The material properties, you can just right click and go to properties, and then it will show you it is a C5000 grade concrete, which is 5000 psi. Then we have a tendon property, tendon material property as defined as a user defined, and we have entered just the modulus of elasticity. Other things kept 0 except the width density here. And one more thing that you can notice here is no matter what stage you are at in the phase of modeling, and if you send your model file to your colleague or other engineers, they can easily keep a track and find out where you have applied what kind of loading, what's the magnitude, what is the boundary condition, what material properties are there in no time. So as I quickly showed you what type of load cases, moving load cases are, where the lanes are located, everything can be easily understood or extracted from the program in no time, just with the help of the workstream menu. So this makes sharing of work very easy. Now coming back to showing you the material properties. So if I want to see what time dependent material properties we are using, I can just double click and it will show me the values as given here. Again, we are using CAB FIP 1990. As you must have seen in different webinars on different type of segmental box girder bridges that we have done in the past, and we will be doing in future. You will be noticing that how we apply time dependent material properties for both creep and shrinkage and gain in compressive strength. And every time we do that, we make it a point to mention that when you are using CBFIP for time dependent material property gain in compressive strength, here you must enter the mean compressive strength of the concrete, which is FCK plus the standard deviation for that concrete, which is 1.166 KSI. So 5 KSI concrete, you need to enter 1.16 something right here. Alright, So that is most of the review that I wanted to share with you. Now we can move on to actually entering the rebar data to this structure. So for this, what we'll do is right click, go to properties, and then we have section manager, where you can define stiffness points, stiffness of the different sections. You may define the reinforcement and the stress point. So today we'll be talking about reinforcement. So I'll click on this, and I'll click on the span, which is the section's name, and you can see this box section right there. Now we'll start entering the longitudinal reinforcement since this tab is activated here. I'll have a guideline so that I know at what depth from the top fiber I am applying the reinforcement, or I could say that how much clear cover I want to have. So 2.3662 is the guideline. So the moment I enter that, you can see this boundary illuminated. This is the guideline at this distance from the outermost periphery, and I'll draw the reinforcement as per line, and I'll click in this field. I click at the corner and then click at the other corner, and then I'll enter the number of rebars as 35. So you can see 35 rebars right there. The diameter for the rebar will be I'll use 4 number rebars, and then I'll click add. That's it. This is how simple modeling or entering the rebar data in Midas Civil. For bottom reinforcement, what I'll do is change the guideline to 1.9685. So this is modified now. I will have 19 at the bottom, 4 number rebar, and then I'll just click at this point and then go all the way across, click at this point and then click add. So when I click here, you can see the area, and click on the other one, you can see the different area right there, 7 and 10.8, and then I'll click apply. So in this manner we have defined the longitudinal reinforcement. Then I'll move on to shear reinforcement, where I'll apply diagonal reinforcement, where the pitch will be 5.91 inches, angle will be 90 degree, and AW is the reinforcement that you are going to enter in as the shear reinforcement. And then we have steel bars for web, and we have torsional reinforcement. So we'll enter just AW and the torsional reinforcement. For this we'll have a pitch of, let's say, 5.91, AWT as 0.6, and ALT as 12.17589. If you don't know the area, you can also decide to click here and select the diameter and the number, and the program will calculate the area and enter it right here for you. But I had these numbers predefined with me, so I just directly go ahead and enter. For torsional reinforcement, there are two reinforcements that we are talking about here. ALT is the longitudinal torsional reinforcement that is entered in the web, and so I was saying that there are two reinforcements that we are considering for torsional, which is AWT and ALT. So basically AW, as we have entered as the diagonal reinforcement right at the top, is the area of vertical rebars which are placed in the web. Alright, and AWT is the area of one-legged outermost closed stirrup. So let me bring back this slide and explain with this with the help of this one. So the outermost closed stirrups that are AWT are the blue circle that you are seeing, right? And then ALT is the hatched box or the broken line rectangular box right here, and they are the longitudinal torsion reinforcement that are distributed around the perimeter of the closed stirrups. So basically these are the closed one-legged stirrups, the blue color ones, and then they are, and the surrounding them or distributed around them are the longitudinal torsion reinforcement. I hope this explanation is clear. So I can go back into the program. If you have any questions and concerns, feel free to ask me, but through the chat window and towards the end of the session, not now. So once we have entered the all the shear reinforcement, I'll click apply and then close it. And if you come to the works tree, you will see under reinforcement it says span, which is the section name, PSC because it's a pre-stressed concrete section, longitudinal is equal to O, and shear is equal to O. It does not mean 0 or null set. O means okay, it has been applied, and if it is not applied, it will show it as an X here, which means a cross, that is, it is not yet applied. So for some sections which for which you haven't defined longitudinal reinforcement or shear reinforcement, you will see an X against shear or longitudinal respectively. Now moving on, so once we have defined the reinforcement, now I can go ahead and modify the construction stage analysis control data. So if I double click here, I click on time dependent effect control, and here you can see there is an option called consider rebar confinement effect. So I'll make sure that it is checked on. By default this option is checked off, so you need to make sure that you are, if you want to consider the effect of rebar confinement, you must check this option on. Then I'll click OK here, click OK here again, and then I'll go to analysis and main analysis control data. Here also there is an option called consider reinforcement for section stiffness calculation. Again, by default this option is checked off. Make sure you have checked this on in order to consider the effect of reinforcement for your section stiffness calculation. Then you can click OK here, and now we are good to perform the analysis and then followed by the design. So I'll click on perform analysis here, and I'll bring up the message window. And here you can see the progress being made. So this construction stage analysis completed, and then the library analysis completed, and the time taken is roughly about 18 seconds. There is a lag between my transmission and your reception, so I'll try to cope up with that. So let me bring up the message window again so that you can see it is actually 17.74 seconds for the analysis. And now we'll go ahead and first define the load combinations. So I'll go to load combination result and combination, and we have some set of load combinations already defined. So what I'll do is go ahead and delete all of them. Now once deleted, we have a special auto generation feature which I'll click on, select the code which is AASHTO LRFD, and then I'll set the construction stage load cases only to be considered for generation of load combinations, and then add on top of them the live load and the other loads. So if I select ST plus CS, this means the static loads and the construction stage loads in the post CS will be duplicated. So in order to avoid that, I'm just using CS only. And then condition for temperature. There are two variations that are possible for load combinations as per AASHTO LRFD. So we'll check on all other effects and then click OK. Now moment we do that, and moreover, if you want to control the values or the components that are there within the load as per AASHTO LRFD, you can expand this dialog box, find the corresponding factors, modify them, and then use it. I mean, you don't have much variation to choose from. They are very straightforward values. You can either choose you want to have the maximum effect or the minimum effect only, or both. Now I'll click OK, and the moment I do that, you can see the load combination is generated in no time. And you can go on, click on each one of the load combinations, and here in the load cases and factors you can see the what load cases are there, what are the factors associated with this. And one thing to be borne in mind is that tendon primary, I mean, whenever we do construction stage analysis, we have tendon forces, creep and shrinkage forces, which have secondary and primary effects. So tendon primary load is not included in the flexural strength check. It is because tendon primary is considered while computing the nominal strength itself, and creep secondary and shrinkage secondary are used for member force calculation. So basically the secondary effects of creep and shrinkage are used for member force calculations. The tendon primary is used to compute the nominal strength of the section, and creep and shrinkage primary effects are used for finding the displacement. So Midas Civil automatically consider these variations in order to generate the load combinations. If you want and you are not satisfied with certain load combinations, you can just click on spreadsheet form, collapse additional tables that you don't need, and then you can go ahead and just like copy paste. You can modify all the load combinations. Just take out all those you don't need, and then you can just play around with them just like in spreadsheets. So and one more thing while defining load combinations is that you have an option called active. Under active you can select whether you want let's say if you don't want a particular load combination or some set of load combinations to be considered while designing, and so you can select those load combination and check on inactive. So basically when the program will do the design, it will ignore those load combinations for checking. The other options available for particular load combinations are it can be strength or state, or the serviceability state. This is strength or stress checking will be done based on this load combination. If you make it serviceability, then it will be used for the serviceability check. So in this manner you can control what you want to, where you want to use the load combinations for. And also when you have certain several load cases within a load combination, then you can choose to have their addition based on just simply add or envelope effect. So you can choose between these two effects in Midas Civil. So this is Midas Civil's auto generation feature. But let's say if you want to create a load combination for your own, then it's very simple. You just go here and find an empty cell, just enter some name, let's say dead. Then you go to load cases, just enter CS dead loads, and then secondary, creep secondary, and shrinkage secondary. and then you can manipulate the factors 1.3, 1.25, 1 and 1, and then just go to the next line and click there. So you get a new load case created for strength check, and this is the factors, the load cases along with the factors in this load combination. But right now I'll just hit delete because I don't want to use it for designing, and then close it. Excuse me. So now I'll move on to perform the design. So you can come find the pre-stress concrete design under design as the first option, and then you can choose pre-stress concrete design parameters. Basically this is the control box for the design that is being performed. You can select the input parameters as what type of tendon you are using, or you are using pre-stressing bars. So we are using low relaxation tendons. What type of bridge are we dealing with? Is it fully pre-stressed concrete or partially pre-stressed concrete? So basically when the bridges are fully pre-stressed, then there are no crack allowed. And when we say partially pre-stressed concrete, then basically we are talking about some sort of cracks are allowed, and then there is something called crack exposure exposure factor for crack width as per LRFD clause 5.7.3.4 that automatically becomes active. So if I say partially PSC, then I can choose from these factors. You can also go ahead and define your own exposure factor for crack width. Then what is the construction type? Is it segmental or non-segmental? So since we are dealing with a segmental bridge, we'll select segmental here. And then what all output you want to extract after the design. You can choose a different set of outputs that you are interested in based on the type of work you are doing. Let's say you are dealing with a very long bridge and you just want to see few things at a given time, so you can just check on those parameters. But I would say it will never hurt if you perform the entire design and save the results later on for usage. So no matter what you want to see, you will get everything right there. So you can easily use unselect all or select all features in order to extract all the results that are there. Then for flexure strength computation, we have the code based method or strain compatibility for more refined analysis. So and the code method is pretty simple, straightforward, based on clause 5.7.3.2 of AASHTO LRFD that you can use. And then corrosion conditions are always there. You can use severe or moderate. Having said that, I'll just go ahead and click OK. Then come to design, and then design pre-stressed concrete design material. Here I'll select the concrete material that I have and make sure that we have correct grade of rebar selected. For main rebar and sub rebar we are using grade 60. You can select from different codes the material property and grade of steel that is there for rebars, and then assign them here, and then click modify and close. Then the next option is, one more thing you should appreciate here is all the steps that are involved to do the design are laid down in a sequential manner in this context menu. So first you define the parameters, next you define the material properties for design, and then you define which element and which position of that element you want to perform the pre-stressed concrete design. So basically, if you want to see or perform the design of particular locations, let me first activate the support so that I can know where the interior supports are. So you can see the support locations. Let me go to this elevation. Let's say if you want to see the do the design of the sections over interior support, and let's say you want to do the design of the mid span. So you can just select these locations and say, okay, I want to do the design for these elements at I and J for moment and not for shear, or none for shear. Then click apply, and let's say you want to do the design for shear or check for shear only at the first two members right there. So you can just go here and select I don't want to have any movement there, but I want to have the shear check at I and J, and then click apply. So once you do that, the program will create a table for you where it will show you which element you have selected, what you want to check at given cross section. But I would say usually this step is not necessary, so I'll just select the entire thing and hit delete from the keyboard. If you don't enter any particular member for design check, the program by default performs the design check of all the previous concrete sections that are there in your model file, and then shows you in the table format. But there is one more step called, or let me follow the same routine. The next step is position for PSC output. Now this step is a bit crucial because usually we want to perform the design of the entire bridge, but when we want to generate the report, we don't want to generate the report for the entire length of the bridge. Few sections are critical. We want to see the calculations and everything spit out in the report or the calculation sheet. So you can specify those members and then just prepare the report or extract the results in the spreadsheet format for those locations. And in this step, if you miss out this step or if you don't enter any member, then the program, if you generate the report, you will get no values for these. I mean, you will get no member displayed. So in this step, it is mandatory that you define the locations for where you want to see the results for in the report formation, or just select the entire thing just by clicking on select all and then clicking apply. So the program will, while producing the report, will generate the report for all the cross sections, I mean all the entire length of the bridge at both I and J, and will show the report for all these the checks that we have performed. But for the time, what I'll do, I'll just select few members. Let's say member number 16, 17, 26 and 27, 36 and 37, which are at the interior support 1 midspan, and then on the right side of the other interior support, and then I'll just click apply. So when I'll generate the report, I'll get the report generated for these locations. And let me now go ahead and tell you about PSC segment assignment. Now what happens is, when a particular portion of the bridge is erected in one shot, or you want to treat number of elements into as one segment, then this feature is very useful. You can select, let's say, these number of elements, consider them as one segment. So program will replace all these segment with one all these elements with one segment. So now this will be the I end and this will be the J end of the entire segment, and this segment will be treated as one member for design. So you'll get the result, one set of result for this, second set of result for the others, and third for the third one. But if the division of the elements that you have done is same as your real construction methodology, so which means that each segment or each element represents one segment, then you need not do this step. So what I'll do is just click here and delete it. So I'm not doing any segment assignment right now because each element represent one segment. And if I let's say if I further divide this segment into number of pieces, then I want to consider this complete set of elements as one segment, then I'll have to use this feature. So now moving on with the pre-stress concrete design, then pre-stress design table is kept there just to make sure that you have done these two steps. Design option is where you want to perform design. If you don't select any member, then the design is performed by default for the entire segment. Then PSC print position or option is uh, to specify for which element locations you want to generate the report. If you select none under this, then the report will have no values in there. So it is mandatory that you select those members or the entire bridge if you want to get the reports in the spreadsheet format. We have done these two steps, so now we can click on PSC Design. And once the design is completed, you will see in the message window right here that the design check has been completed. So you can see here reading PSC design result successfully done. And now we can go to design, PSC design, and directly come on to PSC design calculation. So if I click on design calculation here and click OK, the program will start generating a design report for me that will include all the members that are that I specified. And so while this report is being generated, what I'll do is go to PSC design and see other results. So you come to PSC design result table, you click on check stresses for cross section and at a construction stage, and the program will show you the table as shown here. Let me put this dialog box right at the top here, so when it will be done completed, it will be shown here. So here if you see, we first show the element number, then the part, that means I and J end, and then we'll show the result for both compression and tension, and which stage the maximum value was achieved, and whether the check is OK or NG. NG means not good. FT here represents the stresses at the top fiber, FB means bottom fiber, and FTL means top left, top right, bottom right, and maximum of all these 6 points. And then the allowable value from the code is given, and then you can compare Fmax and allowable. If Fmax is greater than allowable, then this entire row will be turned into red color, and under check you will see NG written here. And each construction stage is shown here, so you can see the stresses at a cross section under construction at a construction stage. Then then you can check the tensile stress for pre-stressing tendons. Again, click OK here. So now this tendon shows the tendon name. FTL1 means the stresses in the tendon after anchor set close to the anchors. And FDL2 is somewhere along the length of the tendon, the maximum stress that is coming after the anchor set. And FLL1 is after all the losses that have occurred in the tendon, what is the stresses left at somewhere along the length of the tendon. And AFDL1, AFDL2 and AFLL1 are the allowable limits as per the codes. So you can see that these limits are not exceeded. If they were exceeded, that particular tendon would be shown in red color right here. Then we'll see some more results. So check stress for cross section at service loads. Oops, I think I checked on the, close this, excuse me. So check stress at a cross for cross section at service loads. So basically here you are seeing the stress check at service loads. And here it shows the load combination name. I mean the first three rows, column head remaining same, element, part, and compression or tension, and load combination name here that caused this worst case scenario. Type, under type it means the moving vehicle load case. So with every with moving vehicle load there are 6 results associated: fx, fy, fz, mx, my, mz, and with each one of these there are two extremes or two envelopes: minimum or maximum effect. So fx minimum, fx maximum, mx minimum, my mx maximum, my minimum, my maximum, and so on and so forth. I'll come to the design report in a little while. Let me minimize it. So basically, out of these 12 cases that are possible from live load, the program picks the one case that caused the worst case scenario for that load combination, and then it gives the complete result. And FT means top fiber stresses, bottom fiber stresses, top left, bottom left, top right, bottom right, maximum, and the allowable value. So, and all these load combinations are the ones that were given for serviceability. So if you see load combination 32 is given right here, which is service 1, and these are the factors that are associated. And if anything goes wrong and is not satisfied, it will show it red color and NG. Then let's see some more results. Then principal stress at a construction stage. It is only the tensile principal stress that we are looking at, and basically for that construction stage which has sigma max being achieved, the program goes to that construction stage and then shows the tensile stress at different locations all around the periphery of the cross section. So you can see P1, P2, P3, P4, P5, P6, P7, P8, P9, and P10 are basically, if you come to model view, right click, go to stresses and beam stresses PSC, you will see these are the 10-point locations where the program has performed this check: point 1, point 2, point 3, point 4, point 5, point 6, 7, 8, 9, and 10. So these are the points all around the periphery where the program has performed this check and then given the worst case condition and then given the sigma maximum value against sigma allowable as per code. Excuse me. After this we'll see principal stress at service loads with excluding torsional shear stress. So again these are the tensile principal stresses but excluding the torsional shear stresses. And the previous one was for construction stage, this is for service loads, and again these load combinations correspond to serviceability check, and the type is again for the live loads, which particular case out of those 12 case possible in this live load was contributed to the worst case scenario. And again deciphering this is absolutely easy. Then you can come to principal stresses, again tensile stresses at service loads. That was for construction stages. This was for service loads excluding torsion. This is including torsion and everything at service loads. And then we'll move on to the strength check. So flexure strength check for both positive and negative, and you can see here this particular segment number 3 at jth end for negative bending moment under load combination 14 and live load type fx minimum is not good. Let us explore why. So the first column that you see, MUY, it is the factored uh, bending moment that is coming onto the section. Let me change the unit to foot and kips. Foot kips. This is the cracking moment for the section. This is the nominal moment resistance. This is the factored nominal resistance, and this is the ratio of ultimate or the external moment that is acting onto the section divided by the phi times the nominal, that is the factored nominal resistance. So whenever this factor is this factor and this factor, basically phi m and y, which is the factored nominal resistance divided by minimum of 1.33 of MUY or 1.2 times of cracking moment is goes below 1, the section shows it as not good section, as you can see here. So all these sections that are shown here are failing under this load combination for negative moment and this moving load case. Then similarly we can have the shear strength check, and again it is the shear that is coming onto the structure, the shear from the bending moment onto this section. This is nominal resistance. This is the resistance factor as per code. This is the nominal resistance from concrete, from shear reinforcement. This VP is from the nominal shear resistance from the pre-stressing. This is the factor nominal resistance. DE is the effective depth from the compressive fiber, extreme most compression fiber to the centroid of the tensile reinforcement. dV is the effective shear depth. EX is the strain, longitudinal strain, and then there are other factors. But something more important, or you will be looking forward to, will be AVS, which is the shear reinforcement that you have applied. Let me change it to inch square so you can see these values. So this is the shear reinforcement that you applied. This is AL, which is the longitudinal torsional reinforcement that you applied, and BV is the width of the cross section or the web where which has been corrected for the duct spacing, or the duct diameter has been taken out from this width. So this is the effective width, and then the program suggests that this is the required shear reinforcement for this section. This is the minimum shear reinforcement as per code, and this is the minimum torsional shear reinforcement that was needed. So clearly, since we applied more than what was required, we are on the safer side as far as shear check is considered. So therefore you are not getting any red line in there. They're all black. This means all are okay. And then last but not the least, combined shear and torsion strength can be checked. Again, as per the AASHTO LRFD here. So you can see the external moment, or in the shear in the moment and the torsion that are coming, the nominal shear and the torsions for the resistance values for the section, the factors, and from the concrete, from the shear reinforcement, from the pre-stressing tendons. So basically all these factors are given here, and you can see the checks are qualified. And more details of this these column heads are given in the tutorial so you can download the tutorial and you can see all the formulations in detail and everything. And now let me bring up the report that was generated for this particular section. So this is the element number, the material property, and which load case we are looking at. All the variables for that cross section have been explained here. The formulation has been given here, and the checks are performed. So what we provided, what is required, it's less than what we what is required is less than what we provided, so therefore check is okay. So all these, this is a detailed report that you will see, which is generated by the program with all the formulations as per clauses and why the check is okay. So you can pick the critical sections that you are curious and then generate this kind of report in no time, and then assess whether the program has done the check properly or not, or if you have missed out something or somewhere something is incorrect or not good. You can even check whether the sections are oversafe and reach to an optimal design through a little bit of iteration process for concrete sections, because this will tell you whether your section is good or not, and once it says not good, then you can investigate what can be the causes, and then based on that you can either modify the geometry or change the section dimensions, or reduce the precessing or increase the precessing, or add or take out the rebars from those particular sections. And this tool is the PSC design tool is very helpful for reaching these kinds of iterations and converging the design in no time. So this was all I wish to cover today. If you have any questions, we can take up now, or you can write all the questions to me and I'll be more than happy to answer them individually. So I'll bring up my contact details on the screen. You can note them down. You can download what all we covered today in tutorial format from our website, which is www.midasuser.com, and from there you can download these tutorials and practice at your own time. So thanks for joining in today.